directly is the mechanical level. Yes, very. Okay, and we're going to continue our talk. The last time we talked about this is the stress for this beam, motional shear. So this power, speed, and torque. We talk about all these things. So as I said, these are power, speed, torque, and they are very, very important because usually when you design a mechanical system, sometimes you will include this is some this is a rotor, some this is a motor, some this is a top, that means power, the shaft. When you design the shaft, you need to know the power, speed, and torque. This is example. Have you guys taken a look at this example? Where? No. Okay.
I had a question about it.
This one, right?
Yeah.
Okay.
In the solution, it shows that there's a difference between like torque and moment. Could you describe what the difference between torque and moment is?
Torque and moment is the same.
They're the same.
Yeah, same. Sometimes the torque we want the twisting torque. That's a twisting moment.
Okay.
They have the same unit.
Right.
They have the same significance. Okay. So some people use moment. Moment that means you want to twist something, right? That's as a torque. The same thing.
Yeah, because it labels them as two different things.
Yeah. This it's okay. That's the same thing. Yeah, the same thing. Interchangeable. It's totally interchangeable. One more time. The torque and the moment, you can use them interchangeably. Okay. So no worries. Don't panic. Torque is you apply. Moment is also you apply, and these two guys achieve the same thing. What's achievement? And twist something. So just the portion, give some portion. The same thing. Thank you very much. What's your name?
Clayton.
Clayton? Clay?
Clayton.
Clayton?
Yes.
I'm from Clayton? Okay.
Yes.
Okay. I'm recognizing your name now, okay guys? If we ask your name, don't panic. So I'm going to talk about this one very briefly. So here, this one is an example. So this is the commonly used one. So I have a beam here, and then I have an arm, and so outside this arm, I have another arm. Right? So I have another arm. So the geometry of this beam is given. The geometry of this one is given also. And however, I apply the load on this small arm. So how to do these things? So you can see, I have a force, the 300-pound force. So you need to know that if you use US customary units, you need to be consistent. Okay. If you change to if you mingle US customary units and international units together, I'm 100% sure your answers will be wrong. Why? Because there is a conversion, there is a factor included. So to be consistent, and you need to use either US customary units for all these variables, or you use international units for all variables. This is very, very important. We are mechanical engineers. Units play a very, very important role. Right? Yeah, so let's see. Draw the free body diagram, compute the maximum torsional stress, and locate the stress elements on the torus surface. We know that based on our experience, if we apply load vertically down, so this point is the first point to break. Right? So this point, if it breaks. So this point A. Why? Because if we apply load, and we will have a torque. So this force is not applied directly on this point. So however, you can see the distance, and we have a torque, and we also this force will be applied here, and in addition, we will have a torque. So this torque is from the force F. So I'm going to talk about this one very, very briefly. Here, look at this diagram. So this is the arm. This is a bigger arm. So this is the beam. This is a bigger beam. for the bigger arm, guys. So as we see in the previous figure, so here is a small arm. The force is applied on the small arm instead of this arm, right? You guys agree? So as a result, so we can the result of the effect of this applied force will be that you move the force to this point on this bigger arm, and you must have a torque generated by this is the complicated form. You guys agree? So when we have the F here and also TC here, and because this force is applied on this point instead of on C. Now we want to move this concentrated force to the C point, and so you must include the effect, the torquing, this is a twisting effect of this F, which equals F multiplied by the effective distance from the point of interest C and to the point where you apply the load. You guys agree? Okay, so that's the reason we have a F here. So this is a TC, and TC is because of this F. And we use the right-handed rule, right? Right-handed rule. So because this F tends to rotate this B clockwise from this angle, clockwise. That's the reason. And so if I use the right-handed rule, so this is my rotational direction. So this makes thumb points in the direction of the moment of the torque. So that's the reason we have it's a TC here. Question? No question? So no question. Let's come back to the B, the point B here. The point B, where the point this F, if we move the F here, so here, there because this B, this arm, this big arm, I'm talking about this big arm. This big arm is in the state of equilibrium. So on the point B, there must be a force pointing up and to balance this F. So that's the reason we have this F here. Right? You understand? So this F used to balance this F, and also because you have a TC, which is a resultant the torque from the contributor for TC, and you must have a T1 which is balancing TC. So in addition, so because here, okay, even though you apply this F here, you put this F here, so this F, this C and B, they have distance. So this the effect of this F on the point B, and you have another torque, another moment, which equals the F multiplied by the distance of this F to this B. I'm talking about the effective distance, which equals 4 inch. That's the reason we have this is M1. So you can see this torque, this one is going to rotate. It's going to rotate this point B in that direction. As a result, to balance this M1, it must be in the opposite direction in order to balance this is F. Question? So this is the this is the Newton's third law. Moment, this is the action and the reaction. So these two guys are always the same in magnitude, however, opposite in direction. Right? So this is how we get. So this is the free body diagram. So F equals 300. So J direction, and it's a vertical direction minus J because that is because the Y, the positive Y is going up. So TC negative 450K. So this one TC. How to calculate this one? So this one multiplied by, so this is 1.5. So this moment will be counter force each. And so BC, for BC, F is the same, M1, right? So this is M1 equals this F multiplied by the distance, F is 300. So distance from this point to this point, I'm talking about the effective distance, that is 4 inch. And that's the reason we get 1200 I on force in the I direction. Bobby.
Why is the F negative for C and but it's positive for.
This is F, right?
Yeah.
So this F is going down, negative. However, you have a reaction force F for B. So because you have F, and there must be the opposite F to balance this original F. Right? Yeah, so it's a T1 equals T1 equals TC in magnitude, but in opposite direction. Questions? At point B of this is here. For here, and we will have this is the this is T2, okay? This is T2, and this T2 equals this is a T2 because and this one because the F and the F multiplied by the 4 equals negative 1200. So this T2, okay, this is T2 balance. This is M1. This is, they are the same. They the same in magnitude. So this, we have M2 here. So this is M2 because F, okay, if you have F and F multiplied by so this is 5 multiplied by sorry. So this is 1.5. This is the, let's look at here. So this 1.5 here. So 1.5 multiplied by 300. So this is because so this F, okay, this F is applied on this point. So at this point, so this can generate a moment in this direction. This direction that is at point B here will be M2. And this M2 equals this F multiplied by effective distance 1.5, which gives us this is a 400K. You understand, alright? Yeah, for the point A, we will have F here. We have MA used to balance this M2. This is the TA balance T2. So here is the MA here, and this MA equals this MA. You use the balance, okay? 1.5 is 1.5 and plus 5, 6.5 multiplied by 300. Understand, guys? So one more time, guys. So we have MA here. Where this MA and this MA is because this I, okay? So this I is acting on here. If we just look at this guy, so this I in fact is that we have I put this I here, and then we need to have additional is a bending moment which equals the total the effective distance from A to F, which equals I5 plus 1.5, totally 6.5, then multiplied by 300. So this gives us 1950. Moment. Whenever you calculate the moment, make sure you calculate the effective distance from the point of interest to the point of where you apply this original force F. Questions? Are you guys following me? Okay, so next one, so this is the free body diagram. Free body diagram is the most important thing. Otherwise, you find the volume calculations will be wrong. So for point B here, BC here, for the arm BC, so the bending moment, which we show maximum near the shaft at the point B here. If we use this one, this is the bending moment, and then the bending stress for the rectangular section. For the rectangular section, can be calculated using this one. rectangular section, so it's about this arm. So the base is 1/4 and height is 1 and 1/4. 1 and 1/4. So you can use this equation to calculate. Questions? Then they say this statement this is not exactly correct. Why? Because the part B they might be welded together. They are not the same, not the same thing. And we are talking about the weldment a little bit in the following course, in the following class. Questions? No questions. So look at this the torsional stress, and you can use this torsional stress use this equation. And it is a T, okay? The T equals 450. So because why? Because we have F equals 300, the torque bending moment or the twisting moment equals 450. You just plug in that equation and you can get this tau maximum. Then we look at this as a point A, and which is the first point to fill. For stress element at A, okay, so we have the bending because this F here, bending moment at F, because of F, this bending moment equals M divided by I. C. I is area moment of inertia. C is the radius here. For this is cross-sectional, circular cross-section. C equals radius. If we use the D, okay, and we have this. So how we get this one? So because the I and the I equals this pi e power 4 and 64. So this is I. And J equals 2 double I. I didn't tell you for circular cross section. And C here and C equals half D. So that's the reason we put I and C in this equation. We have this 32. So this is the pi, and this bending moment equals 1950. Why? How can we get this one bending moment? And because 5 multiplied by 5 plus 1.5 equals 6.5, and 6.5 multiplied by 300 equals 9050. So this is how we get this is 9050. The torsional stress. The torsional stress on this point, this is circular, equals T J over slash C. Okay, so this is torque, and torque equals this is 1200. And how to calculate 300 F multiplied by 4? So that is the twisting torque. So this is a twisting torque. We just plug in, and you have PSI. So we have sigma x and tau x z. So sigma x in the normal and tau x z, and it's in the x in this direction, but also in the z direction. The normal of this plane is in x direction, but this actual stress direction is in the z. That means x z. So this is a plane is x z. We have sigma, we have tau. Then we have sigma, we have tau. We can use this equation to calculate this is a principal normal stress, maximum principal stress. Guys, do still remember how to calculate this is the principal stress? And we use this equation, okay? Because we only have the sigma normal stress and tau. We have sigma and tau. So these are only two is the stress components, and all other components are equal to 0. So we just use this equation to calculate this is sigma 1. Sigma 1 is the maximum principal stress. So then we calculate this is the maximum shear stress. Also, the same thing, maximum shear stress. You guys know the Mohr circle, right? Mohr circle. Mohr circle. Have you learned this one? No? Okay. Mohr circle is a graphical representation of this is the stress, is the transformation. Usually in the CAE, and I taught this Mohr circle. So this is how we calculate, this is a sigma. And Mohr circle says this. So we have, so this is the tau, and so this is the sigma. Right? So we have this is the stress state, and so we have a Mohr circle. So in this direction, we only have stress. So this one will be our sigma 1. Sigma 1 is the maximum principal stress. So here is sigma, for this 2D, we say sigma 2. So this is another principal stress. And so here is a tau, so this is tau 1 and tau 1. And we can say tau 1, we can also say tau maximum. So here is and tau minimum. So suppose this is the stress state. This is our stress state. We have sigma, we have a tau. Right? So we have a sigma and we have a tau. Now, and we can calculate. So this is sigma 1. Because you have not learned this one, so I will hope you guys pay attention to what I say, okay? So this is our sigma and tau. So for our case, and this is the sigma. So our sigma x, so our sigma will be 40.1 and KSI, and our tau is this is a 14 minus 14 and 0.5 and KSI. So let me change this one a little bit. So this is so this is my point. I want to make sure. So this is my point, okay? So because so we have these actual values. So this is my point. Now, if I know this point, based on this one, based on this circle, I can calculate sigma 1. How can I calculate sigma 1? Can somebody tell me based on trigonometry? Can somebody tell me if I know the coordinates of this point, which equals sigma and tau, and how can I calculate sigma 1, and how can I calculate tau maximum? Bobby.
Like Pythagorean theorem.
Yeah, Pythagorean theorem, right? And we will use the Pythagorean theorem. See, so I know sigma 1 equals the radius of this one, right? So sigma 1, this is my sigma 1, and sigma 1 equals this. Do you guys agree? Now, because I know this point, I can draw a vertical line here. So this vertical line here, so this one will be my sigma. Right? You guys agree? And so this guy will be my sigma. And what about this? So this one will be my tau, right? So I would say because it's negative, I just put an absolute sign here. You guys agree? And then how can I calculate the sigma 1? So sigma 1 equals the r, the radius of this circle, and equals the sigma and plus the tau square. Right? Okay. And sigma plus tau square. So this is the I only have tau here. I did so tau z equals 0. So this one and tau z equals 0, right? And then I only have the tau. This is the non-zero one. So I know this the center equals 0. So that's the reason is the tau this one equals 0. So this is sigma 1 equals this is a sigma square plus sigma square plus this one. What? So this is a sigma 1 equals so you can see sigma square plus sigma. So this is the radius. The radius. So this is the radius. And radius plus. So this is original sigma x. Sorry, I must make some mistake.
It's an adjustment factor because the center of the circle isn't at 0, 0.
Yes, so this is without loss of generality, I should use this with a non-zero. Right, so this is should be this point should be the sigma. So this point should be a sigma half is a sigma. Half sigma. This point should be the half sigma. And then the half sigma x, this point half sigma and 0. So this point. So this half sigma then plus this radius. The radius we just calculated. Yes, this one. I'm sorry. So this is sigma 1. Sigma 1 equals half sigma and plus this is r equals sigma x plus half plus this one. So this is sigma x squared. This the center is the sigma. This the center is a sigma. Center is a half sigma plus this is a sigma x plus tau. So here is the assumption is a sigma x is the only non-zero one. Non-zero normal stress. So this is how we calculate this is sigma 1, right? So this is half sigma is the center, and sigma x squared plus tau squared. So this is the Mohr circle. So after get this Mohr circle, So this is the tall one. The tall one, okay, you can see based on circle. So this radius equals this radius. Is the tall maximum equals this one. This is the tall one equals this one. So this is tall square. Tau square plus this is sigma x squared. So this is about this example, and if you have any questions, come to see me. So in the mechanical solids, you have taken mechanical solids, right? So have you in the Moore circle was not taught in that course?
It was like mentioned, but yeah, it's like the last thing we did. Yeah.
Okay, so next Monday I'm going to talk about 10 minutes to talk about it. Okay, so I think it is very, very important. Who taught this course? Taught the mechanical solid?
Dr.
Civil engineering professor. Okay, so I'm going to talk about that one. I can give you some kind of new advance. And then we come back to these tools. These tools. So for this one, what I want to say is that some students ask me, how can we use this equation? So this equation says that we have a tau here, okay? So we have a tau. So this area of this material equals ds multiplied by this is ds multiplied by thickness, and ds multiplied by the t, right? So this is a force. You guys agree? ds multiplied by t, this is this area. Area multiplied by tau is force, right? And force multiplied by this r is moment, right? So this is moment. So we just do the integration. So this moment is used to balance the externally applied moment t. So that's the reason we have because the tau and t, we just take them out. Is a tau and t r ds is r. This r if we use this is a medium line. So suppose we have a medium line here. So we have this one can be calculated 2 am tau t. Based on this equation, if we know the capital T torque, we can calculate this is the tau. So please know that this am is area enclosed by the section, the medium line. So this the area of enclosed by this line, not enclosed by this line, or either this line or this line, but this line. Be very, very careful. Questions? No question? Let's take a look at the next one. So this is the solve. You can use this equation to solve for tau, and you can also calculate. This is a theta 1. Okay, this is a twisting angle, angular twisting angle. We call this is also the displacement, but angular displacement. So this guy can be used calculated using this equation. So please know that this LM is the length of the section median line. So LM, the M stands for the section of the section median line. So this is a dotted line. If you don't use the inner line, don't use the outer line. If you use either inner line or outer line, and your answers will be somehow the. Okay, so this is DAM also equals 1/2 RTS. Questions regarding this one? No question? No question? So here is one example. So this is a SimWatt is a tool. SimWatt tool. And what I want to emphasize is that for this one, you need to calculate the median line, okay? How to calculate median line is? So I give you this dimension. So this dimension, the median line is here. Be very, very careful. I will not go through in detail, but I want to emphasize the importance that you just use the median line instead of outer line or the inner line. Okay. So you can see how to calculate AM. AM is area enclosed by the median line. For our case, the area you need to draw a median line and then calculate this is enclosed area. For the torque LM also you need to calculate. And we will have the similar example, the homework problem to solve. I hope you guys know that. Questions? No question? And then we can, this one is the open seam wall sections. Previous one is closed, but now this open, we have a little bit of slit or a little bit of gap. So this is a small gap, and they make a bigger difference. So this is an open section and some common open seam wall section. So this one is extreme, okay? This one is extreme, and so this is a C. So this is L. This is because the beam we can just see because it is not closed, and so we can see this guy is a special case. But this one, we have a tube, but we have a small slit here. So this is a separate gap, and so we can this C can also be treated as this is open circle. Right? So you can see this one here is not the enclosed. This one is not enclosed either, but this one is not enclosed either. So how to calculate the torsional shear stress? And we use this equation. Tau G is the shear modulus based on the material. And theta 1, this theta 1 is angle of twist per unit length. And the C is the C, the thickness. The 3T multiplied by LC squared. So remember, L is the length of the median line, and C is the wall thickness. And keep this in mind, okay? Otherwise, your answer might be wrong. So L is the length of median line, and C is the wall thickness. For this case, it is wall thickness. For this one, is wall thickness. So shear stress, you can see the shear stress is inversely proportional to the C squared. You can see the angle of the twist, theta, is inversely proportional to C cubic. This is theta. Okay, why? Because you can, based on this equation, you can just put the G and C from here, and this is part of the denominator here. You can see C equals 3T divided by G L C cubic. That is why we say inversely proportional to C cubic. Questions? For small wall thickness, that means if the C is very small, you can see, and the stress and twist can become quite large. Based on this equation, if the C is very, very small, the smaller, the higher the stress will be for the torque level. So compare the thin runner tube with and without a slit. Ratio of wall thickness to outside diameter of 0.1. So this is stress with a slit so high. Okay, twist with a slit is so high. It's very, very high. It's a twist angle. This is the stress. You understand to you guys? So even though you have very, very small slit, the gap is very, very small, but you can increase the stress by this factor. That is horrible. Sometimes it's very, very nasty. This example is a beam, and the geometry is given. And the allowable shear stress is given, the shear modulus is given also, and feather torque corresponding to the allowable shear stress, the angle twist in degrees. And you also use this equation and this equation. Right? So for the 347 is here is. but you need to have this equation, okay, guys? The T equals this one C. After get this T, suppose this is tau. This you can see allowable shear stress. So this allowable shear stress you just plug in. So this is the tau. This is the torque, and that is allowed. And the theta equals theta 1 multiplied by L. The theta 1 is the angular displacement twist per unit volume. So you need to multiply the total twisting angle, the total the twist displacement equals theta 1 multiplied by the total length, longitudinal length. So this is here. A torsional spring rate KT torsional can be expressed as a T torque, applied torque divided by the corresponding theta for this one. Questions? No question? And then from equation 3 is 40, and you can have this one 340, that is the previous one, and we do not treat this one as the open seamward specimen. We just treat this for 340. Here we just treat it as a beam, and that means this beam can be treated as open seamward the structure, or can be treated this one. So we can use two approaches to solve the problem. Then you can compare. Questions? No question? No question. Let's move on to the next one. The stress concentration. You know the stress concentration, right? Stress concentration, if we have some defects, so around these defects, the stress level will be very, very high. So this is called the stress concentration. And so stress concentration is denoted as a sigma maximum because of the defect. Here we use a hole to stand for, and divided by sigma 0. If sigma 0 is if we do not have, this is a defect, what kind of stress level we have? So this is the ratio of sigma maximum divided by sigma 0. So we call this as the stress concentration factor. So we have stress concentration factor. We also have another stress intensity factor. And so this is two different things, right? So we have the stress intensity factor. So this is also use the K. And so this is Ki and K2 and K3. So this is the fracture, this is a crack. Crack is the opening. First mode, I told you 3 modes, right? Manufacturing, guys. In manufacturing, we have 3 opening mode or 3 modes. One is opening, one is sliding, and third one is out of plane tearing. So this is K1, K2, K3. So these 3 guys, they are called stress intensity factor. This is related to the fracture. So these 3 guys are related to the fracture, cracker propagation. But here, it is a stress intensity factor, stress concentration factor. They are related somehow, but they are clear-cut distinct to each other. Okay, don't be confused. So theoretical stress concentration factor, you can see theoretical, this is a hole based on the hole's geometry, and you can get this stress intensity factor. So from these 2 appendices, you can get common examples. And many more in Peterson stress factor. If you use just the Google, you have you can get a very, very useful website that you can specify the geometry of defects, then you can get the stress concentration factor. So note that the trend for this is a higher KT at sharp discontinuity radius and at a greater disruption. So that's the reason we do not like this is a sharp angle. the sharp angle is always a problem, the troublemaker in terms of the stress intensity factor because it is geometrical singularity. Right? So techniques to reduce stress concentration, for example, increase radius and make the radius is a little bit bigger. Reduce disruption. Reduce disruption means that the change of the geometry is kind of smooth instead of round. Right? Another way is allow dead zones to shape our flow lines more gradually. You can see this one. Large radius relief through the shoulder. We have a shoulder. See, we have a shoulder here, and to relieve through shoulder relief through, and we have a sharp angle here. But we supposedly we should remove this sharp angle. Otherwise, so this step, if this step is too, this is too singular, that is a bad power. That can be bad. Very bad. So that means this angle should not be very sharp. So the stress in pressurized cylinder, I'm just to give you these equations, okay? So suppose we have this cylinder, and we have inner pressure, we have outer pressure, and we can use these two equations to calculate. This is the stress, and one is tangential, and one is a radial, and so these two guys are perpendicular to each other. And I just give you this equation, two equations, and I will not test your understanding, but if there's a need, you can come back to calculate. This is analytical on the solution. So this is the special case of zero outside pressure. If P0 equal P outside equals 0, and this is a tangential stress and a radial stress can be expressed using these two equations. You can see it reduced gradually. So this is the sigma T tangential. So this is the sigma R is a radial. So if the both ends are closed, MC. So this we have a cylinder. If both of these cylinder ends they are closed, and so then longitudinal stress can be calculated this one. Longitudinal that is perpendicular to these two ends. So this is a seam wall is a vessel. Is a vessel. We talk about seam wall is a structure. Now this is a vessel. A seam wall vessel. How one can we call this a seam wall vessel? That means if this wall thickness is 1/10 with respect to the radius. That means if the wall thickness, the ratio of the wall thickness to the radius is less than 1/10. And so this is called a seam wall vessel. So radial stress is quite small compared to tangential stress because it is very thin. And so in this condition, so the tangential stress can be calculated using this one, maximum tangential stress and longitudinal stress if the ends they are closed. So this equation I just give you guys, I will not test your understanding. So here's an example. I'm going to this is give this example also. The stress for in rotating the rooms, rotating rooms just like the flywheels, blowers, these things. And the tangential and radial stress are similar to seam wall pressure cylinders, except caused by inertial force. We have inertial force. So this is the stress levels. It is stress sigma T and sigma R. So press and the shrink of fixed. So these if these are two components they are making together. So we will have the P here, okay? And P and the pressure as the interface and A. So this we want to feed these two guys together. So this is P equals this equation delta. You can see delta is a difference between this is outer diameter and the inner diameter of this guy.